Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. Next-generation geothermal power from companies like Fervo, Eavor, and Quaise is gaining attention for baseload electricity generation. That's because it promises to tap into a nearly unlimited supply of free, clean energy that previously we didn't have the technology to access. Today I'll walk you through the innovations of each company, their strengths and weaknesses, and how long it could be before we see next-generation geothermal at scale. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. First, the reason I've chosen Fervo, Eavor, and Quaise is because they've received a lot of press. There are other companies working on geothermal, but by covering three of the most talked about companies, it'll provide a good overview of the next generation geothermal industry as a whole. Let's start by taking a look at how conventional geothermal works, and then do a mini deep dive into how companies like Fervo, Eavor, and Quaise are approaching geothermal. Conventional geothermal power generation involves tapping into shallow hydrothermal reservoirs, that is, high-temperature water reservoirs that are near the surface of the Earth's crust. That high-temperature water is used to spin a turbine to generate electricity, which can be done in three ways. First, for super hot reservoirs, dry steam can be used directly from the reservoir. This method is the simplest and most efficient, but super hot reservoirs with the right geology are rare. Second, for slightly cooler, hot reservoirs with clean water, high-temperature, high-pressure water can be brought to the surface and flashed into steam. This is the most common type of geothermal because it's relatively simple and efficient, and the suitable reservoir geology is more common. That is, it's a good balance of cost and resource availability. Third, for lower temperature hydrothermal reservoirs, or reservoirs with salty or corrosive water, the water from the reservoir is brought to the surface and run through a heat exchanger, which is called a binary cycle. The heat exchanger contains an organic fluid with a low boiling point, like isobutane, which is vaporized to spin the turbine generator. The lower temperature requirement means this method can be used in more reservoirs, but the higher capital costs and complexity of the heat exchanger result in electricity costs that aren't competitive, so it's seen limited deployment. Overall, as you can see on screen, regardless of whether dry steam, flash steam, or binary generation is used, geothermal resources are relatively geographically limited. And where there are opportunities, it doesn't always coincide with population centers and therefore infrastructure for low-cost integration into the grid. So, in order to reduce the cost of geothermal and increase the areas where it's viable, new methods are required to reduce the cost of drilling and operation. With all that in mind, let's take a look at Fervo, Eavor, and Quaise, which are each innovating in their own way with drilling and well design so that low-cost geothermal can be built nearly anywhere. Fervo's geothermal works by drilling two wells in parallel to each other in dry rock, and then drilling horizontally and fracturing, or fracking, the rock using high-pressure water and sand. After that, plain water is injected into one of the wells. That water permeates into the fractured rock, which heats it, and then is recovered by the parallel production well. It's then pumped to the surface, and a binary cycle is used to spin a turbine generator. Horizontal drilling and fracking were of course pioneered by the oil and gas industry over the past couple of decades to increase the output of each well drilled, and now Fervo is leveraging that technology for geothermal drilling. Let's take a look at how that works. The deeper a geothermal well is drilled, the hotter the rock, which is good for efficiency. However, the rock also becomes denser with depth. The denser and hotter rock is more difficult to drill through, which is expensive. By drilling deep enough to reach rock that's just hot enough for geothermal, then drilling horizontally, it allows the well to be made longer for the same cost, meaning more surface area to heat the injection water more quickly, meaning more energy that can be brought to the surface to spin the turbine. And, of course, fracking pulverizes the rock, which further increases its surface area and allows the water to absorb even more heat energy as it moves from the injection well to the production well. Fracking does, of course, introduce risks, but it's not as bad as oil industry fracking. That's for two reasons. First, Fervo's fracking is much less extensive than oil industry fracking. Second, it's occurring in dry rock rather than petroleum-containing rocks that can seep and release toxic hydrocarbons into water supplies. The last note on Fervo is that, as I said a moment ago, they're using a binary cycle, or heat exchanger, which adds cost and complexity. That cost and complexity is offset by the lower cost of the drilling, and using a binary cycle will allow Fervo to drill geothermal wells nearly anywhere and at shallower depths by using cooler geothermal resources. Next, let's look at Eavor. Eavor also drills in hot, dry rock and uses horizontal drilling. However, instead of two parallel wells with no branching, they drill multi-branched wells that connect at the tips to form closed loops. After creating the loops, they seal the rock walls of the borehole, turning it into what they call rock pipe. That is, it's a fully closed system that doesn't allow the water that's pumped through the geothermal system to seep into the surrounding rock. Again, after the water is injected and retrieved from the geothermal loop, a binary cycle is used to convert the thermal energy into electricity. The benefit of Eavor's approach is that it has almost no subsurface or seismic side effects because it's fully self-contained, and it allows for a thermosiphon effect. That is, the cold water introduced at the surface will naturally sink, and as it heats, it naturally rises on the production side of the closed loop. That means very little active pumping is required to run the system because it's passively pumped through the geothermal loop due to thermodynamics. The drawback of Eavor's approach is that much more drilling is required to achieve the same surface area as Fervo's system. It's technically more difficult to make the perfect underground loops, and blockages are a potential issue because the water has to rely on one return pathway rather than hundreds of potential pathways that are possible with Fervo's fracking method. Lastly, let's look at Quaise. Quaise has by far the greatest science fiction vibes of the three companies, so it's attracted the most attention. For the first few kilometers of their geothermal wells, they use conventional drill bits to auger through softer rock. But once they hit ultra-hot and dense deep rock, they switch to a gyrotron energy beam, which instantly vaporizes the rock. The gyrotron they use is from nuclear fusion research, and it operates on the same principle as a microwave. However, rather than using around 1,000 watts of power at a frequency of around 2.5 gigahertz, it uses 1,000,000 watts at a frequency of around 100 gigahertz. By using a gyrotron to vaporize the rock, there's no longer a drill bit to melt or wear down, so the well can be drilled far deeper than typical geothermal at low cost. That means Quaise can tap into deeper rock that provides super hot geothermal temperatures, meaning a geothermal system with much higher efficiency and lower cost. The vaporization also has the handy side effect of vitrifying the walls of the well. What does that mean? With a typical well, miles of drill pipe have to be intermittently removed to not only replace the drill bit, but also to insert steel casing and concrete to keep the borehole from collapsing. With Quaise, the drilling can occur continuously because there's no drill bit to replace and the sides of the borehole are melted into ultra-hard obsidian, so no casing is required. The end result is that Quaise should be able to drill through ultra-dense hot rock 10 to 50 times faster than conventional drilling, roughly 3 to 5 meters per hour instead of 0.1 meters per hour, which means a 10-kilometer deep borehole could be drilled in 10 days instead of 10 years. What about drawbacks? Quaise isn't just adapting existing drilling technologies to a new use case, they're developing an entirely new way of drilling. And along with that means a raft of new engineering challenges. Let's take a look at 3 quick examples. The first challenge is avoiding plasma generation in the borehole that could melt the boring equipment. The second is removing the vaporized rock and ash from the bottom of the borehole, which is several miles deep. Third, injecting hot water so deep into such hot rock could create issues for the stability of the borehole. On that note, Quaise expects their geothermal operations to create supercritical steam. That is, steam that's at extraordinary temperatures and pressures. Much like Fervo, they intend to drill parallel boreholes and fracture the rock between them close to the bottom of the borehole. But when the water is pumped into the injection well, it won't remain as water, but will instead turn into supercritical steam, which will allow them to extract up to 10 times more energy when it's piped up from the production well. Once that supercritical steam reaches the surface, it will again go through a heat exchanger, but instead of flashing a chemical like isobutane, the supercritical steam will be hot enough to flash water to steam to drive the turbine generator. Why not just use the supercritical steam directly to drive the turbine? Because the supercritical steam will contain corrosive compounds that would damage the turbine. Overall, if Quaise can get this technology working, it could ultimately be the cheapest, cleanest, most power-dense, and most geographically flexible geothermal technology. The question is, how long will it take, and how much will the electricity cost? Let's compare each of the technologies. Starting with cost, Fervo is targeting $100 per megawatt hour in the next few years, and $50 per megawatt hour in the 2030s. The estimated electricity cost from Eavor's test facility is over $200 per megawatt hour, but they claim to have line of sight to $75 per megawatt hour. Meanwhile, Quaise has given a range of estimates from $20 to $115 per megawatt hour. That is, they don't really know yet because their technology is still under development. For comparison, both solar and gas turbine generation are currently around $100 per megawatt hour. You'll often see lower costs mentioned for each, but it often doesn't take into account the cost of firming for solar power and recent increases in the cost of gas turbine generators due to data center demand. In terms of progress and scaling, Fervo's Project Red test site in Nevada was able to hit a maximum of 3.5 megawatts of electrical power in stress testing, and in continuous operation delivers a steady-state average of 1.4 megawatts, which is used to offset Google's local data center demand. Fervo is now working on a full-scale facility in Utah that's targeting 100 megawatts of steady-state power by 2027. Then 500 megawatts by 2028, and long-term up to 2 gigawatts at that site. As for Eavor, their test site in Germany was targeting 8.2 megawatts of electrical power, but fell severely short at between half and 2 megawatts of electrical power. As a result, they're backing away from building the geothermal plants themselves and looking to license their drilling technology instead. As for Quaise, they haven't yet started to scale because they're still working through engineering challenges. Their goal is to have a 50 megawatt geothermal well operating and producing power by 2030, but I expect that timeline to slip. Overall, if all goes well, my expectation for all 3 of these companies combined is to hit maybe 1 gigawatt of next-generation geothermal power by 2030. In summary, next-generation geothermal power includes an array of technologies that solve the geographic limitations of conventional geothermal by allowing geothermal energy to be tapped into nearly anywhere and at low cost. Some of those technologies, like Quaise Energy's gyrotron drilling, are still some years away. But others, like Fervo's horizontal drilling and fracking, are successfully past the prototype stage and are ready for major power production. So if all goes well, we should see Fervo's technology start to scale in earnest in the next few years, and from there it could scale rapidly. That's because the equipment and knowledge are widely available from the oil and gas industry, and it only takes Fervo a few weeks to drill a well. The time-consuming part is things like permitting and connecting to the grid. As for cost, it looks like $100 per megawatt-hour is in the bag, which is competitive with solar and gas. And in the longer term, with scale, they could provide some of the cheapest and cleanest power available at closer to $50 per megawatt-hour. As a final note, geothermal power is a great complement to solar power because it can provide baseload rather than intermittent power. The other major options for baseload generation are gas and next-generation nuclear, but I suspect that geothermal will eventually gain broader appeal. That's because gas generation faces noise and air pollution concerns, and next-generation nuclear faces larger challenges with engineering and financing. As always, that's what seems likely to me, and it's not an indication of personal preference. I'm energy agnostic because we need as much energy as possible from every available technology because energy governs economic growth and prosperity. So it's a great time to be an energy nerd because there are exciting developments in every generation type, whether that be nuclear, fuel cells, gas, solar, batteries, or geothermal. As always, please consider supporting the channel with the links in the description, which now also includes a referral link for Signature Solar. If you use that link to purchase home battery or solar equipment, it nets me a small percent-based credit, but that can add up on a large purchase and it really helps the channel. On that note, a special thanks to my YouTube members, ex-subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.